Group 91 presenting the paper titled Deja Vu, Continual Model Generalization for Unseen Domains. In online learning scenarios, training data changes over time. Deep learning models might handle small changes, but big shifts like seeing completely new data or seeing messy or biased data can cause them to perform poorly. Models struggle to quickly adapt to these new situations, and in doing so, they may forget what they've already learned. Continuously upgrading models is expensive and also requires a lot of storage. There are models to implement this task of incremental learning, but they have certain limitations. And the limitations include domain adaptation. Traditional domain adaptation needs access to original training data, which isn't always feasible. Test time or online DA improves the model with minimal data but shows limited gains unless the large data volumes are available. A key issue across these methods is poor performance during the unfamiliar periods. When the model first encounters drastically different data, this is critical in areas like environmental surveillance and medical imaging, etc. The second limitation is domain generalization. Attempting to generalize the model in all types of domain can lead to catastrophic forgetting and previously learned domains. Unified DA and DG approaches are still inherent limitations of standard methods. While some models handle gradual changes in the data, they fail to adapt to sudden large shifts. These issues make the existing DG method less effective in real-world settings with continual and unpredictable data changes. This is the overview of the framework that is enacted on in this paper. What we do is we have two domains, a source domain and a target domain. Source domain contains labeled samples and target domain contains unlabeled samples. First, we apply a rand mix algorithm, which actually adds noise to the images present in the source domain or the data present in the source domain. And using the probability distribution that we see in the source domain, we generate new synthetic labels. And we then try to extract some measures like mean or covariance or other such similarity measures, and we store them. On the target domain, we also apply the same initial setup like adding noise and creating synthetic labels. But what we do is we use the stored measures from the label domain to perform the classification on the target domain. We can see here the dashed line represents the existing method, and in the unfamiliar period, the accuracy of the in the unfamiliar period we can see that the accuracy of the existing method drops, but the solid line that represents the proposed RATP method that is shown in this paper does not cause the drop in accuracy in the unfamiliar period, and it's actually an improvement on the existing methods. Now the RATP first component is random mix-up augmentation. The problem for which random mix-up augmentation or rand mix is used is that we want to generalize our model to unseen domain from a single source domain. How we try to do that is we try to generate new augmentations of the originally present data by trying to add some noise to it and by using lightweight autoencoders. Now, autoencoders used in rand mix is to generate augmented data that helps to improve models generalization across domain. It does this by encoding source domain data and decoding it back into new representation, introducing variability to make the model more robust. Noise is added through ADA in adaptive instance normalization. It injects randomness with a very small variance into the autoencoder. By generating two noisy inputs using linear layers, which are then injected into autoencoder's representation as a multiplicative and additive noise.
Now moving to the second part of RATP, that is top to pseudo labeling T2PL. The problem here is to provide accurate pseudo labels for the unlabeled target domains, because our target domain doesn't have labels. So for that we are applying top to pseudo labeling. The objective of top to pseudo labeling in random mix is to mitigate the risk of error propagation when dealing with target domains when updating. It aims to augment a subset of the target domain data rather than full set to avoid relying on potentially unreliable pseudo labels. T2PL selects target data based on the prediction confidence, only augmenting samples for which the model confidence exceeds a threshold, for example, 0.8 we can take. This reduces the risk of incorporating noisy or incorrect labels during training, ensuring that the augmented data is both useful and accurate for model adaptation. Our approach here is we are applying here is a softmax confidence to identify first the top 50% of the samples for centroid construction, and after that we are applying weighted aggregation to compute the class centroid. Here is the formula. And moving on, we have refined selection using cosine similarity and assign labels via k nearest neighbors. And after applying them, we found the result as more accurate pseudo labels for the reliable adaptation.
Okay, the third component of our ATP model is prototype contrastive alignment or PCA. It solves the problem of cross-domain alignment without worsening the adaptivity gaps. Prototype contrastive alignment or PCA is a type of prototype alignment learning technique. It is used for addressing challenges like cross-domain sample variability and data insufficiency. It aligns domains to improve models' ability to generalize across varying data distribution and aims to enhance models' performance by ensuring better domain adaptation. PCA improves cross-domain alignment by optimizing domain-specific prototypes rather than averaging prototypes across domains. PCA maximizes the similarity between samples and their own domains prototypes. Using contrastive learning, it distinguishes between classes by incorporating negative pairs. The overall objective combines cross-entropy loss, PCA loss, and knowledge distillation loss, ensuring better prototype alignment and improved generalization across domains. The model that this paper works on worked on dataset consisting of digits dataset, PAX dataset, and domain net. A ResNet model was used to train upon this dataset on PAX and domain net, and a DTN was used as the feature extractor for digits. This training split was 80-20. RATP is compared across several state-of-the-art models across various domains. The the performance matrix shows the performance of different models across different data sets. The bold blue uh, the bold blue numbers represent the best performing models, and the bold black numbers represent the second best performing models. You can see that the models trained by this dataset have mostly the bold blue assignment that represent this is one of the best performing dataset on all of the domain. These are the effectiveness of different modules in RATP. Now, effectiveness of rand mix uh, is shown by the fact that on removing the rand mix from RATP, the performance of the model decreases significantly, and attaching rand mix other than baseline models clearly improves the model's performance. Effectiveness of T2PL is justified by the fact that when T2PL is replaced in RATP with other pseudo labeling approaches, the model of the accuracy of the model decreases significantly, and RATP performs the best when it has T2PL. Effectiveness of PCA is shown by the fact that RATP performance degrades considerably without LPCA, and when we used other methods instead of it, the performance remains worse. This validates the effectiveness of PCA. And these are the different graphs showing the performance of different components of. Now, in concluding the presentation, we say that by integrating a training-free data augmentation on the mod like rand mix and pseudo labeling mechanism and a prototype contrastive alignment algorithm, RATP enhances generalization, target domain adaptation, and forgetting elevation, that we also say catastrophic forgetting. The RATP demonstrates significant performance improvement in handling domain shifts. It also in practical scenarios it performs very well, and its applicability is very high across diverse datasets and challenges. Thank you.